In the last video we showed how to convert an nth order initial value problem, so a single nth order differential equation, into a system of n first order differential equations. And then now we're going to show through several examples how we can solve those systems. So we're going to use the same problem, which I'll go over in a second. First we'll solve it using the first order explicit method, and then the first order implicit method, and then crank Nicholson, the three methods that we went through in a series of videos before this. So this is a second order initial value problem. So that means that capital N is equal to 2. All right, so capital N is equal to 2. So it's d squared u dt squared is equal to minus u. So we have the highest order derivative on the left, and then anything involving the independent variable, dependent variable, up to the first derivative on the right. So the f is minus u of t. And we have two initial conditions because it's second order, so we need 2. So we have u at 0, 0, and du dt at 0 is 1. So there's the initial position is 0 and the initial velocity is 1. So you should be able to solve this using Math 252 techniques, and you get the exact solution that u is equal to sine of t, and so we'll use that for comparison. All right, so we're going to convert this second order equation, n is equal to 2, into two first order equations. So the method that we discussed last time is we define two variables, u1 and u2. u1 is simply the same as the original dependent variable u, and then u2 is the same as its first derivative, so du dt. Then we take our transformation, which is what this is, differentiate the first equation. So u1 is u, so u1 dot is u dot, but u dot is just u2. So u1 dot is equal to u2. Again, we get rid of this because it's in the old variable. We don't want that. When we write everything in terms of the new variables, u1 and u2. The second equation is u2 is equal to u dot, or du dt. So u2 dot is u double dot, differentiating that. But u double dot, well, that's just d squared u dt squared. That's minus u. So minus u, but u is u1. So it's minus u1. So again, get rid of all this intermediate stuff, and we have the final system is u1 dot is equal to u2, and u2 dot is equal to minus u1. So that's our system of equations. We can write that in matrix form down here. We'll come back to those initial conditions in a second. So we have the matrix form of, well, let's forget the initial conditions. We have the matrix form of that system of two equations for two unknowns. On the left we have u1 dot, u2 dot, and it's equal to 0. The first equation, u1 dot, is equal to 0 times u1 plus 1 times u2. The second equation is u2 dot is equal to minus u1 plus 0 times u2. Okay, now the initial conditions, remember we had u at 0 is 0, u dot at 0 is 1. So we translate those into the new variables, which means that u1 of 0 is 0 and u2 of 0 is 1, which is written here as a vector. So the vector u1, u2 is equal to 0, 1 at t is equal to 0. All right, so here's the two equations I just went through. So u1 dot is equal to u2, and u2 dot is equal to minus u1. So again, we have one second order equation converted to two first order equations, and now we're going to solve it, in this case using the first order explicit method. Okay, so in the first order explicit method, we approximate the equation at the old time step tn, and we do that using a forward difference. So in the first order explicit method, we've already done all the hard work. Now we're just applying the same equations, but now to two equations instead of one. So on the left, we have du1 dt, which we write at using a forward difference as u1n plus 1 minus u1n over delta t, and that's equal to u2n. So that's this first equation written at the previous time step. Then the second equation is du2 dt is equal to minus u1. So we have the forward difference for u2, so u2n plus 1 minus u2n over delta t is equal to minus u1, again, n at the previous time step. We write the difference equation with the unknown on the left and all the knowns on the right. For an explicit method, we only have one unknown on the left, everything else is on the right. One unknown on the left, everything else is known on the right. Okay, now the initial conditions, the general form, we had A1 and A2. Now those are 0 and 1. So that's what we'll use throughout. So essentially, the way we would solve this is just like where we just had one equation, but now with two, we get the value of u1 and u2 at n, and then we update it using these right-hand sides to get the new values of u1 and u2 at the next time step. And we just march forward like that. Just like with a single equation, this is only conditionally stable. So the first order implicit method, remember that was to address the stability issue, still only first order accurate. We use the same second order initial value problem that we did in the previous example, which I've repeated here. So you can look back and you can see, same problem, same underlying equations, different methods, and you can see how these compare. So in the first order implicit method, remember that we approximate the equation at the next time level, tn plus 1 instead of tn. So now we're using a backward difference for the time derivative instead of a forward difference. So this is now a backward difference on the left for u1 and u2, and then the right-hand side is just the u2 and the minus u1, and they're evaluated now at the new time level, which we don't know. So when we pull the unknowns to the left and knowns to the right, now we have more unknowns and only one known. More unknowns and only one known. So just remember the pattern. Don't memorize these things. Don't overanalyze it. Just remember the pattern. Remember where the approximation is done in order to get these. Pull the unknowns to the left, you get what you get. You don't have to just let it follow from the method. Okay, so let's write these now in matrix form. So in matrix form, we have a 2 by 2 matrix times the u1 and the u2 at the n plus first time level is equal to u1, u2. Now you notice in the previous case, we had the vector, the n plus first time step for u1 and 2 was equal to a matrix times u1 and u2 at the previous. Now that matrix is on the left-hand side instead of on the right-hand side. So we have to solve the system of equations in a coupled fashion, just like we did back in chapter 2, I believe it was, solving systems of equations. Obviously these are just numbers, the delta t's minus delta t's, those are just numbers. So we can take the inverse of this, or however we want to solve it, and get the solution for u1, u2 at the new time level. And then again, you just do that over and over again. So every time step, you're going to solve this system of equations again. Notice the coefficient matrix doesn't change. The only thing that changes is this right-hand side vector, and therefore the solution. So remember from our discussion at the time, if you have a situation where only the right-hand side vector is changing and not the coefficient coefficient matrix, there are certain methods that are very amenable to that. So there's LU decomposition, Kramer's rule is not great. So LU decomposition, and the other one was, my mind is going blank. I need some sugar. All right, so that is the equation that we solve, system of equations that we solve at every time step to advance and march the solution forward. This is unconditionally stable. So the first order implicit method is unconditionally stable. Then the Crank-Nicholson method, so remember Crank-Nicholson method upgrades the first order implicit method to second order accuracy as opposed to first order accuracy. So it's implicit, so it has the favorable numerical stability properties, but it is also better in terms of accuracy. So again, same second order initial value problem, which has been converted into a system of two first order equations. Now for Nicholson, remember we approximated at the midpoint, the mid-time between the previous and the current time step. So we have an average. So on the left, we have a central difference for du1 dt and du2 dt. And then we have an average on the right. So this is u2 on the right here, so it's the average of u2 at n and u2n plus 1. That's why I divide by 2, because we're taking an average. That gives us an approximation for u2 at the midpoint between the two time steps. Same thing here. Then, as always, bring the unknowns to the left, the knowns to the right, and this is what we end up with. Once again, we have a system of equations in matrix form. It now looks like this, and you'll notice we now have a coefficient matrix on the left, and we have a matrix on the right, coefficient matrix on the right. So we solve it the same way. Notice neither of these matrices changes when you go from time step to time step. So you could take the inverse of this and bring it over, multiply these two together, they don't change, and then you can solve one after the other, the system of equations one after the other, to march the solution forward in time. Again, it is second order accurate now in time, and it's unconditionally stable. So it's a little bit harder, a little bit more work than any of the other two methods, but again, the gain is better accuracy and better stability. So you'll notice that these implicit methods, so first order implicit method and Nicholson method, when applied to a system of first order equations, leads to essentially, so if you remember our numerical solution procedure, steps 1, 2, and 3, so step 3 involves solving a linear algebraic system of equations if the original differential equation was linear. If not, then it's a nonlinear system. So these single-step methods, I haven't brought this up, but we call them self-starting. So what that means is you can start with the initial condition at t is equal to 0, move forward in time without any other intermediate techniques just to get the method started. And that's because they only involve one time step. And so you have the initial condition, then you advance it one time step. You don't need anything beyond that. So it's self-starting. And in fact, you can adjust the delta t as you go. So if you find that your delta t is too big, for accuracy reasons, as you go, you can make it smaller, you can make it bigger, so it computes faster, whatever the situation might be. All right, and we'll look at another example in the next, actually two examples in the next video.